All right, so today we're talking about Hess's Law. We're talking about enthalpies in chemical reactions. So one of your aspects of thermochemistry is how much heat is released or how much heat is required over the course of a reaction. So here's an example of reaction. We have sodium chloride reacts with calcium hydroxide. It's going to produce calcium chloride and sodium hydroxide. So this is a simple double replacement reaction. But the question is, hey, what's the enthalpy change for this reaction? And so we're going to go about solving this using something from our data booklet. Your data booklet in Chemistry 30 has a list of all your standard enthalpies of formation for many common compounds. And so this is where we're going to use our knowledge about thermodynamics. One of the first laws of thermodynamics is energy can't be created or destroyed. So if there's an energy change in this reaction, well then every single one of those reactants and products requires energy to form their compounds from elements. This table tells you how much energy is required to form each of those compounds. So for example, from that table, sodium chloride, to form it from its elements, I'm not going to balance it, but the delta H for formation is going to be negative 411.2. Maybe we will balance it, it's pretty easy. That's the enthalpy of formation. That's kilojoules per mole of forming this stuff, right? The calcium hydroxide. So we have calcium hydroxide has an enthalpy of formation of negative 985.2 kilojoules per mole. So again, that means if we took calcium and we took oxygen and we took hydrogen and we formed this from its elements, it would release this much energy. Every mole of this thing that gets produced would release this much energy. On the products, our calcium chloride has a delta H for formation of negative 795.4 kilojoules per mole. Same thing, that's telling you this is how much energy is released when this compound, a mole of it, forms from its elements. And then the last one, we have sodium hydroxide. So again, formed from its elements. So we should put 2's here to balance it. The delta H for formation is negative 425.8 kilojoules per mole. So keep that in mind. That's our first part of the question. We have to figure out what those enthalpies of formation are, and they all just come from this table. You just look for the name of your compound, you make sure the chemical formula matches. If there was water, we pay special attention to water. There's different enthalpies of formation for liquid and gas because energy is required to go from different states of matter, and energy is released when different bonds are formed and things like this. So in the different states of matter, we have different enthalpies of formation because different enthalpies, different energies would be required to create the compound in a different state. So these are the things that we need to solve this question. Because again, returning to our idea of thermodynamics, all of this energy comes from somewhere. And it comes from here. Maybe a better way of saying it is it's accounted for. It's all accounted for here. All of the energy that is present in this reaction can be expressed, therefore, as a difference of the sum of the energies required to form the products and the difference between the sum of energies required to form the reactants as compounds. That will give us the enthalpy for this reaction, because again, just to reiterate the laws of thermodynamics, if all energy is already present, energy cannot be created or destroyed. So the energy in each of these guys, there was energy required to form them. This much energy required to form that. This much energy required to form each of these things. If this energy is required to form those compounds, then the energy for the overall reaction of them reacting together in a new chemical reaction, that net change can be expressed as the difference. Remember, in math, Difference is subtraction, the difference between the sum of their enthalpies before and after the reaction takes place. So let's continue with that. So keep these numbers in mind. We're going to use them again in just a second. So our reaction has NaCl plus CaOH2, CaCl2 plus NaOH. So if I want to sum the reactants, what I'm going to sum, and we know that these are molar enthalpies that we were looking at, so we need to know how many moles are present in the reaction we're considering. This one's pretty easy. All these coefficients are 1 when we see that it's balanced. Oh, it's not balanced. Let's balance it first. 2 Cls, 1 calcium, 2 hydroxides, so we should put a 2 here. 2 hydroxides, and now there's 2 NAs. Good, perfect. So going back to our enthalpies of formation that we've already recorded, the sodium chloride is a reactant, negative 411.2 kilojoules per mole of that, and we have 2 moles present, so multiply it by 2. We're also going to have our calcium hydroxide, has our negative 985.2 kilojoules per mole. We have 1 mole of those. Okay, take out our trusty calculator here. So 411.2 times 2 equals 822.4 kilojoules. This is times 2 moles, so our moles cancel, right? So we have kilojoules. And this guy times 1 is negative, well, from my negative, 95.2 kilojoules. This was times 1 mole, so moles, so it's just kilojoules. If we add those together, 822.4 plus 985.2 leaves us with 1,000. Sum of the reactants enthalpies for formation, 1,000 negative 807.6 kilojoules. We do the same thing for the products. Calcium chloride, negative 795.4 kilojoules per mole times 1 mole, negative 795.4 kilojoules. And the sodium hydroxide, negative 425.8 kilojoules per mole times 2 moles equals 425.8 times 2 equals negative 851.6 kilojoules. Sum those together, the sum of the products is 795.4 plus 851.6 equals still negative 1647 kilojoules. So now our last step, we need to, if now we have the sum of the enthalpies of the products, with the sum of the enthalpies of the reactants, we need to express this as a difference between the two total enthalpies, or energies of formation, however you want to call it. This is how much energy was required to form the products. This is how much energy was required to form the reactants. So if we consider the actual reaction that we're asked to find the delta H for, because the energy had to come from somewhere and it doesn't come from just nowhere at all, we can find the difference between these two, and that will that will realize the net energy change from reactants to products. So it's quite simple from this final step, right? We said the sum of the products minus the sum of the reactants. Again, the trickiest part here is just remembering that you need it balanced so that you have your correct enthalpies for however many moles were present in this equation. Remember, in this equation. So we have our negative 1647 kilojoules. We're going to subtract negative 1807.6. Remember your double negatives here, so this becomes a positive, right? Back to our calculator. Negative 1647 plus 1807.6, or subtract the negative. And we get, this is a positive result. We get positive 160.6 kilojoules. So, returning to the original question, when they say, what is the delta H for the reaction, which we've now balanced, 2NaCl plus CaOH, 2 calcium chloride plus 2NaOH. The delta H is 160.6 kilojoules. Now let's talk a little bit more about why is this positive. All of the other ones, all the formations that we used already earlier in the problem, they were all negative. That meant when we formed these compounds from their elements, when we formed all of those compounds that were reactants or products from their elements, they would have been exothermic reactions. So how come this reaction has a negative thing? Well, I don't know why exactly the result is positive, is not a negative enthalpy. I'm not sure why this reaction in particular is, other than the math, right? But we can talk about what this means. Positive means, well, if the negative indicated a net release of energy to the environment, then the positive means energy is required to make this reaction happen. Let's talk about reactions and reaction progress. So this might be the enthalpies or the energy of our reactants and our products. And this is what we call our big fancy chemistry word is reaction progress, which really just means time. As time continues, the reaction happens, right? So if our products have more enthalpy than our reactants, the delta H is negative and it is exothermic. Now, if our reactants, I think I said that backwards. Sorry, these are our reactants. If our reactants have more energy than our products. There we go. Thank you, everybody who's paying attention. If our reactants have more energy than our products, the release is exothermic. This energy is released. The difference is negative because we'd be summing our products, subtract our reactants, and this is a smaller number than this is, right? Because this is a enthalpy increasing in numbers, right? So so if our reactants have more energy than our products, the difference is negative when we subtract, so it's an exothermic reaction. If the reactants have less energy than the products, well, again, this energy had to come from somewhere. It means we're required to input energy to make this reaction actually happen. The delta H is positive because now when you do products minus reactants, you have a bigger number, subtract a smaller number, and this is what we call endothermic. It's an endothermic reaction. Let's talk a little bit more about these graphs. So we have an exothermic reaction versus an endothermic reaction. So we have time in the reaction and we have delta H. All right, so more energy in the reactants than the products and less energy in the reactants than the products. So what actually happens in this reaction? Normally you'll see these diagrams drawn like this. And we'll say, well, what does that mean, right? So this is still the difference. This is still delta H and it's still positive if it's endothermic. This is still delta H and it's still negative if it's exothermic. So endothermic positive delta H, exothermic negative delta H. What is this? Reactants to peak. Reactants to peak. And on this case, right, it's even higher. It's like that. What is that? That is what we call the activation energy. I was working with a student, we were talking about this the other day. We said, well, what is the activation energy? So the activation energy is the reason why things don't spontaneously combust all around you. So for example, we know a campfire, burning a log would be an exothermic reaction. Any kind of combustion reaction is exothermic. You have to light the fire. Once the log is burning, this is how much heat you'll feel from the fire. The difference between the reactants and the products is how much heat you'll feel. But you have to start that fire. You need to strike a match, for example, or use some kind of fire starter. If you strike a match, you're inputting more energy at the start. That is called the energy of activation. It's similar for an endothermic reaction. The point is that there's more energy required than the net change from reactants to products because activation energy exists. It looks a little kind of wonky in the endothermic reaction because we go, wow, that's a lot of energy kind of thing. But yes, if you don't input more energy than the thing actually requires, the reaction actually requires to absorb, it won't happen. Same here. If you don't put more energy in than the reactants already have, the reaction will not continue on its own and it won't actually release the heat and it won't warm you up. If you don't start your fire, the logs won't light themselves and it won't warm you up. You'll hear the word catalyst. What does a catalyst do? Well, a catalyst is very similar to, it affects the rate of reaction the same way that certain things can affect the rate of dissolving. So we know that if we agitate a mixture, if you're trying to put salt in water and you stir it up, it will dissolve faster. If you heat it up, it will dissolve faster. Those aren't reactions. That's just what we call dissociation, which we'll talk about another time. But it's a similar idea to a catalyst. If you think of that as rate of dissolving, the same things could increase the rate of reaction. So think about when you have one of those endothermic ice packs where you break the packet and the two chemicals mix. It tells you to shake it. Why? Because if you shake it, if you agitate it, more of the chemical will react with the other chemical and the reaction will happen more quickly. But another thing that you can do is you can include a catalyst. The way a catalyst functions is, let's take a look at another one. We'll consider an exothermic reaction. So if this is our reaction, again we call it reaction progress, our chemistry word for time. And this is our energy or enthalpy or whatever we want to call it. So here's our reactants. Here's our product. And we know this is the delta H, but we know that it's actually going to go up and then down because we also have activation energy. Catalyst is going to do two things. The first thing the catalyst is going to do is it's going to reduce the activation energy required. The second thing it's going to do is it's going to speed up the rate of reaction. So we see this time happens before this time. And also this activation energy is lower than this activation energy. So that's where we'd say with a catalyst, two things happen. The reaction is completed quicker or in less time, right? And then the other thing is less activation energy is required. Or you'll see it written sometimes that it reduces the required activation energy. Remember that a catalyst will not be used up or consumed during reaction because it does not react. So the function of a catalyst is going to be a little bit beyond what we covered in high school chemistry, but that's the idea, is it does not get consumed, it does not react. So how would we know one was present? Well, if we return to our original equation, and this is a crucial part here, if there was a catalyst here, it would say something like, I'm going to make up a word and pretend it's a catalyst. I don't know, sometimes I'll write a chemical compound above the line. Sometimes I'll just write catalyst. And writing it above the line it tells us something. It reminds us that this catalyst is not a reactant or a product, but it is present and it is affecting something in the reaction. So that's why we're going to indicate the catalyst is here, and that's how you'll see it. That's how you'll know it's present. But then you might ask, well, wait, what about this guy? What about our delta H? Does this catalyst being present, does this now affect our enthalpy for this reaction, all the steps we just did? Well, let's go back to our diagram to answer that question. What do we notice? The reactants and the products have the same energies that they did before. So the difference between the two, the delta H, is still the same. The only thing that changed was how much activation energy was required and how quickly the reaction was complete. But the start and the end is the same. So in chemistry, when we're talking about how we calculate delta H, you can almost say that it's not the journey, it's the destination in the context of chemistry. Because yes, the reactants and the products have the same enthalpies that they did with or without the catalyst being present. So like we said, that does not affect delta H. So you can calculate delta H exactly the same. If they're telling you a catalyst is present, all that tells you is that there's less activation energy. So this concludes our video on Hess's Law, and of course a little bit on reaction progress, endothermic and exothermic reaction diagrams, and what the presence of a catalyst does during that reaction. We're going to continue here with the other Hess's Law, the Hess's Law that continues about our idea of conservation of energy, and it talks about if we have multiple different reactions, how can we use information about those to find information about something when the compounds present in the reaction that we're looking for are not in our molar enthalpies of formation data table. So we're going to take a look at that in just 1 second.